Well, let's get started. So, hello everyone. Today's lab will be discussing heap sort, another sorting algorithm. So we will see what are the properties. It is based on complete binary tree. What is complete binary tree? Regarding heaps, we have max and min heaps. What is the difference? Also, we can represent heaps as array. How can we represent heap as an array? Also, we see how we can build a heap based on max heap or min heap, okay? And finally, we'll discuss heap sort, and then we compare all the sorting algorithm that we saw so far. Right, so let's get started with the complete binary tree. So we discussed this a bit about in the last lab. So it is very important property of tree for heap data structure. Okay. So can you define what is a complete binary tree? When a tree is said to be completely binary, yes?
A tree that has each parent has 2 children.
Yes, furthermore.
No, it's all.
Exactly. Okay, very important. So what you describe, it's what we call full complete binary tree, okay, where each node has exactly 2 children, okay? But it can also happen that it's not full, but it's still complete, okay? So it's complete when, if you take the tree with height h-1, it is full complete, okay? And then for the last height, okay, you have the elements are fit from the left to the right. Does that make sense? So let's take a look at these trees. Can you tell me which one is completely balanced? Let's start with the tree A. Give me a second. Yes, Vladislav. Yes. So the tree A, is it a complete binary tree or no? Yeah, the first one, this one. Yes, exactly. And Dimitri, so he said it is complete. Okay. But what he said, you said because all the nodes except in the last level are having exactly 2 children. So the tree before the last level is fully complete.
No, because the h-1, like the second level.
If you take, just close this one. Let me, wait a second. Forget about this one, okay? Take a look at this. Is it a complete binary tree? Yes? So what about the last level? Element that fit from the left to the right, yes or no? Does it satisfy the properties of complete binary tree? Yes. So this tree is a complete binary tree, but not a full complete binary tree. Okay. To have it full, we should have also here nodes like this. Okay. Then it will become a full complete binary tree. Does that make sense? Well, Dimitri Alikin. Yes, so what about B? Is it a complete binary tree or not?
The same situation, but the complete first level and the second level. And as for the last level, the second level.
No, because it does not satisfy the last property. You should pay attention here. We say the tree is complete balance, okay? It's complete binary tree. If you have a full binary tree at h-1 level, so all the nodes apart from the last level are having exactly 2 children, okay? Plus, this means if you look at this, you take a look at this part, this is h-1, right? You check that each node is having exactly 2 children in this part. So h-1 is what? Is full complete, okay? But plus in the last level, you should have element filled from the left to the right, okay? In this case, it is from? Yeah, this makes it not complete, okay? Yeah, to have it complete, we should have 8 here, okay? And not here. Does that make sense?
Yes.
Yeah. Mikhail? Zielinski, yes. So what about C? It's complete. It is even full complete, okay? Vitali? Yes. What about the last one? Why?
Because the h-1 level is not full.
Yeah. So it does not satisfy all the properties. Okay. If you take a look at the h-1 tree with height h-1, it's have these empty cells, and then the last row is not filled from the left to the right. Well, let's discuss the heap data structure. So from the lecture and the tutorial, Ivan Chebikin, not here. It's not here, okay. Gregory Phil? Yes, so what can you tell about the heap data structure? Mm-hmm.
So for each node, we have 2 children, and we have the property that the value of node will be the greatest among its children.
Exactly, nice. So it's pretty well said. So you have a heap data structure, which is basically a complete binary tree with one particular property. Each root node is the maximum in the case of max heap, okay, of all its descendants, okay, or it is the minimum in the case of min heap. Does that make sense? So I think he also answered the 2 second questions. Vladimir Rubienkov, not here? Ah, it's you? Yes, so can we implement a heap using an array?
Yes.
How? So yes, we can. How can we calculate the index of each node? Any guess? No, it's not based on hash function. It's like if you have an array, you have like the tree representation, okay, and you have it in an array. What are the properties of the tree? When we have a node, we should know the children or the parent, okay? So if they're inside an array, how can we have access given a node to its parent, its left and right children? Yes? Mm-hmm. Mm-hmm. Yeah. And the parent is? No, the parent is not I. When you're talking about the node I, yeah. Yeah, so the parent is I divided by 2. Okay? We're seeing more in practice. So here you have the properties, how to calculate the indexes. So the root node is always at index 0. Okay? And then for a given node I, if you want to compute the parent, here we assume that we start indexing from 0. It is I minus 1 divided by 2. The left children is 2I plus 1. And the right children is 2I plus 2. This is very important for you because I saw like in the midterm exam, there's this small details that you're missing. Because we will give you exercise based on these properties. You should be able to solve it. For example, you are given this and you're asked to build the mean heap of this array, okay? So since you're given an array, you should know, given a node, how should I get the left children and the right children, right? And how can I get the parent as well? Does that make sense? So if you want to build this, we start with 0, right? We know that 0 is the root node, right? So I start with 0, I will plot 0 here. Okay? And then what is the left and the right side of 0? 0 is index 0. We said that we compute the right children by taking 2I plus 1 and 2I plus 2 for the right one, 2I plus 1 for the left one. So when you take index 0, 2 by 0 plus 1, it gives us, let me write down the indices here. So we have 0, 1, 2, 3. Basically the same as the value that you have there. So when you compute 2I plus 1, it gives you this one, 1, right? So this means that the left children is this 1. The left children is 2 multiplied by 0 plus 2, give us 2, right? So the value 2 should come here. And then I move to the next node. When I take 1, what is the left and the right node of 1? Okay, what is the NX of 1? NX of 1 is, the NX of 1 is 1. When you compute 2I plus 1, 2 multiplied by 1, 2 plus 1, it gives us 3. Okay, so it tells us that 3 is the left children of 1. And then when you compute 2 multiplied by 1 multiplied by 2 plus 2, it gives us 4. Okay, so the right children of 1 is 4. Okay, then you have to compute the left and the right children of 2. Where is 2? 2 is here. The index is 2. Okay, so what is the left children? Is 2 multiplied by 2 plus 1. It gives us 4. 4 plus 1, 5. Okay, so we plot 5 here, and then when we take 2 multiplied by 2 plus 2, it will give us 6. We write 6 there, and so on and so forth. So on and so forth. We see that 3 we have as left children, 7 and 8, and here we have what? 9 and 10. Here we have did I miss something? No, yeah, so we have 11, 12, and then 14. We don't have 14. Okay, so using this property, this is how we can have the array representation of a tree. Okay, we know how to have access to the left, to the right children, and the parent. Let's check the property of the parent. If I choose 6, for example, I want to know what is the parent of 6. 6 is here, right? We said to have the parent, we divide by 2. So we said we divide by I minus 1 divided by 2. If the array is indexed from 0, you have to remove 1 everywhere. Okay, it will be different. If the array is indexed from 1, this value are going to be slightly different.
Should the index of 2?
What? If the array is indexed from 1, the root should be index 1. To have the parent is exactly I divided by 2. The left is 2i and the right is 2i plus 1. This is if the array is indexed from 1, okay? So in my case, the array is indexed from 0. So when I pick up 6, I have 6 minus 1 divided by 2. And we take the biggest value, so it gives us 3. Okay, so it gives us 2. Should be what? Yeah. So we get rid of the door and we have what? Index 2. Okay. When I get 2 divided by 2, okay, 2 minus 1 divided by 2, okay, and we got the round value. And the round value is 0, we have the parent of 1 of 2, which is 0. Does that make sense? So if this is clear, let's move. So you have the array representation that we just built before. Now we have an exercise. So we are given these following numbers, and you are asked to build the max heap from them. So there are things that you should respect when you are inserting inside the max heap. Okay. So let's just copy this. So let me copy them here. So can you tell me what are the numbers? 15, 20, 7, 9, 13. Mm-hmm. 8, right? Yeah, 8. So how do we insert in a max heap? So since one thing that you should know, after every insertion, the tree that you have should be complete binary tree. Okay? This means that the insertion is not the same as in the binary search tree. Okay? So you should not confuse. So every time that you insert to the leftmost free position. Does that make sense? What do I mean from that? Let's build the BST from this sequence. Okay? So the BST will be what? We start with 15, right? We start with 15. And then to insert 20, we go here. To insert 7, we go here. To insert 9, we come here and here. 9. No, to insert 9, we come here and here. To insert 13, we come here and here. To insert 31, we come here, left, right. To insert 50, it will come here. To insert 8, it will come here. Okay? It should be left. I'm not talking about EVL trees. I just said BST, okay? So this is just a classic insertion in BST. We didn't perform the rotations here for EVL tree, okay? So, but the insertion for him, is this tree complete binary tree? It's not complete binary tree, okay? So you cannot perform the insertion as the classic insertion in BST, okay? So how do we insert them? We start from the root node, 15, okay? We have only one element. It is already a heap, a max heap, okay? So remember here we are building a max heap. So, and then when we insert 20, we should insert to the leftmost free position. Does that make sense? So I insert here 20. Okay. Then I should make sure that it satisfies the heap property. We say the max heap property, the root node should be the maximum. Okay. So we perform some swapping by comparing the element that I inserted with its parent. Okay. So I compare what? I compare 20 and 50. What is the biggest? The biggest is 20. So I perform swapping. Okay. So I will swap. Oops. So I will swap, 20 will go as root and 50 will come here. 15 will come here. Okay. Is it a complete binary tree? Yes. Is it a max heap? Yes. Okay. Then I move next. I need to insert which value? 7. Okay. To insert 7, I need to insert it to the leftmost free place. Okay. So I will insert 7 right away here. Okay. Yes. Let's have an array representation as well of this max heap. Okay. So you understand why it is important to have the tree complete balance. So at this point we have what? We have 20, 50, and 7, right? At this point we have this element in the array representation. So when I move to 9, to insert 9, I should insert 9 right away here. Okay. So 9 we go here, 9 we come here. Does that make sense? So just imagine that you inserted 9 somewhere here. Okay. The array will have what? We have 3 cells here, 3 cells here, 3 here, and 9 there. Okay.
In this way, it's not important to be like the right number is just the biggest number. The number is the lower than.
We just pay attention to the maximum number.
Oh, okay.
Okay.
So it's like it's normal if the right node is like lower than.
Exactly.
Okay.
Okay. So it's not a binary search tree. Does that make sense?
Would it be okay to replace, like, swap the two routes? Like the subtree 7 and 9 and 15 will be the same. Will be the same. 7, 9, and then 15. Like the 7 and 9 will be left subtree, and 15 will be.
Yeah. So when you insert, you perform the heap. If you check that it satisfies the heap property. So you check with the parent. If it is less than the parent, you swap until the parent is bigger than the element the current element. Does that make sense? But what I want to show you here is that if it is not complete binary tree, you have an array representation with empty cells. Okay? With non-existing children, left children, and right children. You got the intuition? So we try to insert to the next freemost cells. Okay? To have our array what? Stuck in one place of the array. Does that make sense? So next, so we shouldn't insert 9 there. We should insert 9 here. So we have what here? We have 9. So do we need to swap? No need to swap because 9 is lower than 15. Okay? So we move to the next element. Next element, we insert 30. Insert 30, I insert 30 to the freemost, the next free steps, like the successor, if you can say it like this, okay? So when I insert 30, I should compare it with the parent, okay? And then compare with the root node. How is 30 compared to its parent? It's bigger, okay? So I swap. I will swap here. I will have 30 here. So when I swap, I will have 15 will come here. I compare 30 with 20, 20 will come here, and then 30 will go in a root. Okay? Is it a max heap?
You have to compare with the first part.
Not with the root directly. We compare with the parent and then the parent. Okay? So what does it mean? This means that, let me check, we have 20, we had 9 here. And when I insert 30, 30 comes here, right? Then inside the array, how is it working? Inside the array, I compare 20 with what is the parent? We have what? I minus 1 divided by 2. Okay? It will tell us that the parent of 30 is so what is the parent of 30? Is here, right? And what is this parent? The parent is here. Does that make sense? I told you because the array is indexed from 0. Okay, so remember, when the array is indexed from 0, it is I minus 1 divided by 2. If the array is indexed from 1, you have root is equal to 1. You will have the parent will be equal to what? To I divided by 2. Exactly. You have the left will be equal to 2i, and you have the right will be equal to 2i plus 1. Okay? So if you are said that the array is indexed from 0, 1, you should choose one of these respect accordingly. So inside the array, how is it working? To have access to the parent of 20, I just check here and there, and I perform the swapping inside the array itself. Does that make sense? Well. So the next node to insert is 31, okay? Where will I insert 31? I will insert 31 exactly here, okay? And then I check what? I check the parent and so I insert 31 here, and then I start checking the parent. How is it 31 compared to the parent? It's bigger, okay? So I swap. So I will swap. 7 will come here. $31 will go there. How's 31 compared to 30 is bigger, okay? So we have 30 will come here, and then we swap with 31, okay? So after insertion, I still make sure that I have a complete binary tree, and then it satisfies the max heap property. You have the maximum element in the rows. Does that make sense? And then I move to 50. So when I insert 50, 50 will come here, and then I compare 50 with this node and its parents. So we see that 50 is bigger than 30, which is bigger than 31. So we have what? We will swap. And 30 will come here, 31 will move here, and then 50 will go as a root node. Okay? And finally, I will insert 8. Remember, we insert to the leftmost place. So we have 8 there. After this, we have the max heap. This is our max heap from this sequence. Does that make sense? So is it complete binary tree? Yes. Do we have the maximum element as root node? Yes. Okay. Any question? I hope this is clear. So pay attention. Do not confuse with insertion in binary search tree. Okay. The insertion in Heap is quite different. We pay attention to the fact that the tree should be complete binary tree, not binary search tree. That's a confusion that most of you will be doing. And while inserting, we insert to the leftmost free place in the tree. Okay? So the next insertion will come here, and then here, and then here. So this part of the tree should always be empty. Where's? It may not be complete. It could be, but it may not be. In most cases, it will not be complete. The main difference with? The difference is first, okay? In binary search tree, what do you have? For each node, all the subtree, all the left subtree should be lower than the than that node, okay? And all the right sub-tree should be bigger than that particular node, okay? But for max heap, you have what? A complete binary tree where the root element is the maximum element, or the minimum in the case of min heap. Does that make sense? So please pay attention to this difference. Do not confuse there. So let's get back to the slides. So after doing that, we can represent them in an array. We start doing it before I stopped. So let's just represent this in an array. So I will create the array. So here we have almost 9 elements. So the root node is 50. Okay, so let me index is 0, 1, 2, 3, 4, 5, 6, 7. So the root node is 15. You want to compute the index of the left and the right node. Okay, the left node is what? We have the left. So multiplied by I plus 1, and you have the right. So multiplied by I plus 2. Okay, so you have the left node here 20, and the right node will be 31. Okay, and then you pick up 20. When you pick 20, you use the same formula to compute the left and the right. The index is what? Is 1. The left is 2 by 1 plus 1. So multiplied by 1 plus 1, you will have what? You have 3. Okay, so you insert the left children of 30, which is 9. We insert so you insert 9 here, and then the right children 14. When you pick up 31, you use the same formula. You have 2 by 2 plus 1. It gives us 5. So we will put the left children of 30 there, and then the right children of 30 at index 6. The right children is 30. And finally, we have 8. When we go where? When we come here, we check 9, okay? And you have the left children of 9, which is there. And then the other part, you have nothing left, okay? But just imagine that you didn't have like a complete binary tree, because there's kind of logic behind. So if you had 8 here, this won't be a complete binary tree, but to have the index of 30, you will skip a lot of cells.
If there are empty spaces, yes, then this is not a binary tree.
Exactly. Okay, so if you have to insert 8, what is the index of 30? Is 6, right? So you have 6 by 2 plus 1. Okay, so you have the index 13. Okay, so this means what? This means that you have what? You have a lot of empty cells here until 13 to have 8 there. Okay, and it's not normal. So when you have a complete binary tree, the array representation does not have empty cells in between. Does that make sense? Why? So this is how you can have the array representation. So let's move next. Before that. So now we need to perform like delete operation. So when you are given a heap, we can perform deletion. Okay. So even after deleting an element, you should still have all the heap properties satisfied. Okay. But another thing, another constraint in heap is that we always remove the root node. Okay. So delete operation in heap always remove the root node. Does that make sense? So if I want to delete, when we call delete, this means that we are removing the root node. So if you call delete, it will try to remove what? 50. Okay. So the delete operation here should also preserve the heap property. So to delete, I will do what? I will swap 50 and the leftmost element in the last level, okay? And after swapping, I will then make sure that the heap property is satisfied from the top to the bottom, okay? So when I delete 50, I will swap 50 and 8. So let me duplicate this so that we will see before and after. Copy. So when I call delete in the first time, I will swap. This will swap. It will send what? It will send 8 here and 50 there. Okay. Let's look at it in the array itself. So this means that in my array, I will swap these two cells, right? So I will swap, and then I will have what? I will have 50 will come here. And then I will have 8 here. So after doing that, I can remove this part, right? But this does not satisfy the heap property. Does this satisfy the heap property? No. So we have to perform the operation to make it heap. So from the root to the bottom, we take the root nodes, we compare to the children, and we swap with the children with the maximum value. Okay? So I compare 8 and 30 and 31, 20 and 31, what is the biggest value? 31, so I swap. Yes, exactly. So I swap 8 and 31. So I will have 8 here and 31 here. Okay? And then I swap again. I compare from here. What is the biggest element? Okay? And I swap 8 and 30. So I will have here 30, and here I'll have 8. Does that make sense? So this means that how does it look like in my array? In my array, it means that we had 31 here, 30 came here, and then 8 went there. Okay? So you can see that this still satisfies the heap property. So what do we do? We swap the root element with the last element. Okay? And from the root element, we then heapify by checking that the maximum element is still always the root. We will get back to it. Okay? Heapify, it's an operation to make an array heap, to make a tree as a heap. Okay? So I have a tree which is not a heap, but I heapify. From the root node, I heapify. It's one operation, okay? Where you have to go from the root node to make sure that the maximum is always the root node. Does that make sense? So next, if I call delete again, this means that I'm going to delete 31, right? So to delete, we swap with the last element. Okay? So we will swap 31 and 8. Yeah, you're right. So that this was 7. Yes, this was 7 and this is 8 here. So I will swap 31 and 8. So I will have here 31 and I will have 8 there. Okay. So what does it mean? This means that in my array, I will have what? I will have 31 there and I will have 8 here. And then what we do, we can delete this. And then we heapify from the root node. We check from the root node, what is the maximum? And then we swap. Okay? We see that the maximum is 30. So 30 will come here. So 30 will come here. 8 will go there. And then we compare 8 and 7. 8 is maximum. So we keep like this. We stop there. Does that make sense? So if we call heapify again, delete again, this means that we're going to swap 30 and 7. Okay? Yeah. Yeah, the most right word, because we want to keep the complete binary tree. Okay? So we will swap 7 here and 30 there. So this means that in our array, we have what? We have 30 here and 7 there. And then when you remove this, we heapify again. Okay? We compare these two. What is the maximum? Is 20. Okay? This means that I swap you mean share? So when we swap, we will have here 20 will come here and 7 will go there. Okay? And then we compare, we check again from this substrate. 7 and 15. Okay? What is the maximum? It's 15. So we swap again. 15 will come here. And we have 7 there. So how does it look like in our array? This means that in our array, we have here, we have 7, share 20, and share 50. In the array representation, when we perform the swapping, this is how the array looks like. If we perform delete again, what's the next value that will be deleted? 20. Okay? So we swap. This means we swap these two. Okay? So we swap 7 and 20. So we swap 7 and 20. So 7 comes here. And 20 goes there. So 20 is the element that we deleted. So we have here 20. So this is the same thing that we do here. So we have 7 there and 20. And then we remove 20. Next, we compare the heap property. We check from the children of 7, what is the maximum? It's 15. So we swap here 15. 15 we go there, and 7 we come here. Okay? And then we swap again between these two. Okay? So we have, finally, we have 7 there and 9 there. So in our array representation, this means that after the swapping, we should have what? 15 here, 9, and 7, right? So if we call delete again, what will happen? We will swap 15 and 7. So we have here 7 and 50. So this is the same thing that's going to happen here. So we have here 7 and 50. And then we check, after removing this node, we check the heap property. Between 9 and 8, what is the maximum? It is 9. So we will have what? So we have, yeah, we have 9 here and 7 there. Okay? So we have 9 and 7. If we call delete again, what will happen? Not 9 will be swapped with 8. So we have 9 here. And 8 there. So we remove this one. Oh no, we remove this one. And here we have which value? 8. It's still a heap, okay? And then if we delete again, we swap 8 and, yeah, we swap 8 and 7. So we swap here, we have 8 and 7. This means that we have 8 here and 7 as the root, okay? And finally, if we delete again, we have what? We have 7 and the tree is empty, okay? So this is delete operation. So I have one question for Maxim Oldmanov. Yes. So what can you conclude after deleting all the elements in the max heap? Yeah. So when we delete all the elements and we insert the deleted element in the last 3 cells of the array, move what? We have the same array. We have the array representation of the max heap. Okay. So when we delete, we swap with the leftmost element, right? And then we delete that element. Okay. So after the swapping inside the array, we do this until the array is completely, we swap all the elements and the tree is empty. Okay. So what can you conclude after this operation by looking at the array after the deletion? Min heap? Maybe, yeah. But most importantly, the array is sorted. And this is heap sort. Okay. And this is heap sort because what? We always take up the maximum element. And how is it linked with priority queue? You understand, we will hear about priority queue. Okay. In priority queue, we are given a bunch of number. Okay. Then we say in the priority queue, we want the smallest element is the most preferred. Okay. Has the priority. Like the youngest has the priority in this room. Okay. What does it mean? This means that we will build a min heap. And every time that we call the next element, will be the element with the highest priority. And that element will be the minimum in the case of min heap. If the maximum element is having the highest priority, when we call the next element, it should be the maximum element. Okay? So if you take a look at the max heap itself, it has what as property? It has the fact that we can easily implement priority queues using a max heap or a min heap. Does that make sense? So, and also in a heap data structure, when you insert elements and then you delete them, they will be in a sorted order. Does that make sense? Nice. We have examples for you to practice. So then comes the heapify algorithm. So remember, heapify is one operation that you are given a node, okay? And you want to heapify from that node. You can see this node as the root node, okay? And the heapify, what you will do, you will check the left and the right children, okay? And it will swap the current node with the maximum value, okay? What we did before, okay? But what we did is that we built a heap with insertions. So we saw how we can build a heap by inserting values one by one, okay? But you can be given a tree, okay, which is a BST, and you are asked to heapify that tree, okay? So you perform the heapify operation several times, from the leaves node to the root node. Does that make sense? So you have the heapify max heap that takes what? A tree, which is assumed complete binary tree, okay? And then you goes from the root nodes, from the leaves to the root node, and you call the max heap on those. And then this will do it progressively to the root. Okay? So let's take a look at an example. So if you have this example, this is a tree that we have. Is this a binary search tree? Is it a binary search tree?
Yes.
Well, then, so if you are given such a binary search tree and you are asked to heapify the tree, so we didn't give us a sequence of elements. So you know how to build a tree, a heap from a sequence of elements, right? So when you insert, you heapify, okay? But if you are given a tree and you are asked to build a heap from that tree, you should heapify several times, okay? So you should heapify n time exactly. So let's go from the, I guess I have it here. So this is the tree that we have here, okay? It's a binary search tree, which is also complete. Because if it's not complete, we cannot perform the heap on that, okay? So to heapify, we start from the leaves node. So if you want to heapify this node, it's already heapified, right? Because it's only one element. This one is also already heapified, okay? This one and this one. So all the last row is already heapified. Does that make sense? After heapifying a node, that node should be the root of a heap. Yes, the substrate.
So we'll take number 3.
It has no children, so it's already a heap. It has only one element, okay? So then we move here, okay? And we want to heapify from here. So heapify from this node means what? Means checking its children and swapping the maximum value with itself, with that root element, okay? So what does it mean? This means that after heapifying, when heapifying, we will swap here and here. So here we have what? 40 and 12, okay? And then we come here to this node. We check the children. It's already the maximum. The maximum is 5, okay? So we swap what? 5 and 4, okay? So we swap here. Here we have here is 14 and 12. Okay? And then we check the root node. Okay? When we check the root node, we compare this one with this one. Okay? So we have what? We swap 14 and 8. So I will swap here. I will have 14, and here we have what? 8. And then we need to check again because this substrate is not heap. Okay? So when we go from here, we go to the leaves. Okay? So when we check here, 12 and 8, 12 is the maximum. So we have here 12, and here we have 8. And then I heapified a binary search tree to a heap. Does that make sense? So what is the time complexity of heapify? Why should be n log n? You have n, like it is sequential. When you have a node, you know what is the parent and what is the left children. So if you are given exactly an array, yeah, the heapify operation itself. Yes. The heapify is linear. Okay? Why heapify is linear? If I am given an array, okay, the representation is an array. Can I heapify in linear time? But we start from this, and then we check this one, and then we check this one, and then we check this one. Okay? So basically we start from high minus 1. Okay? And then what we do, we check this one and each children. If they are not, we swap, right? And then we swap, we check this one and its children. If they are not, we swap. And then we go to the root element. We again need to check this one and this one. Why n log n? The heapify operation itself.
We discussed one when we take the value and put it in the right place. So for one,
Only 4?
next for I of one node.
No, you are given an array. You are given an array and you are asked to heapify. Can you heapify in linear time?
Keep in mind your time for keep. Because the next one is it's a very not the words then
Maybe just as I understood, we did not understand correctly the algorithm, because as far as I understood, we need to check all the nodes that are lower than node we check. For example, when we check the root node, we check the node that is lower and lower.
So
This algorithm I see in
I'm talking about the heapify to build a heap. Okay, so to heapify to build a heap, we should go through all the nodes. So take a look at this implementation here.
This implementation is linear. In what you showed, we take one node. It's what you have in the right, and in the left, where
when we take one node, this is what we do.
Yes, and as you shown, here I see that it's working linear time, but you show
This can be what's the time of this?
heapify.
This is heapify. It's log n. When you have a node and you heapify. But if you want to build, if you want to build a tree, if you want to heapify a tree, like heapify the entire tree, this is linear. Because you do heapify how many times? Yeah. So basically you end up having linear time complexity. Okay, so let's first analyze the time complexity of all the operations. We start with insertion. So when we insert in a, can I have it? Things are a bit weird here. So let me build a tree here. Oh no, that's not the max heap. So what is the time complexity of insertion in a heap? It is log n, okay? Because when we insert, if we insert, for example, 60 here, okay, we will check with its parent, 1 comparison, 2 comparison, 3 comparison, okay? So basically the maximum of the comparison depends on the height of the tree, okay? So what about delayed operation? Is logarithm of n. Then what is the time complexity of sorting, heap sort? Why? Wait, I want someone else to answer this. Wait, why not log n? Adelina, is she here? No? It is what?
No, I mean, even now.
Andrei Milevsky? No? Ruslan Abdulin? Is he here? No? Marcel? Marcel Gamulin? No? Let me put the 0. Ikram Kamat? Is it the right group?
Yes. You're just like.
Paulina? Bazenova? Yes. So why Heapify is n log n? Can you describe how does it works, heap sort? No idea? Victor Danilem? Grigory Butnik is not here. Yeah. Sergey Gubin? Yes. So why heap sort is n log n? Maybe first recap what we discussed about heap sort. How is it working? How does it sort the sequence? Can you speak a bit loudly? Yes, after you put the number in the heap, so after you put the number in the heap, the array sorted, right? So analyze the term complexity. Why is it n log n? Yes.
The worst case, yes.
Wait. So here we have the tree, we have the heap, okay? We said delete operation. What is the term complexity of delete? Is log n, okay? So to delete, we swap with the leftmost. Okay, so when I delete, I will have what? I will have 50 here, and then I will have 8 here. Okay, so I will remove this one, and then I need to maintain the heap property. So I will heapify from 8. Okay, so heapify from 8 will make me swap 8 with 31 because it's the largest. Okay, so we have 8 here, 31 here, and then we swap again 8 and 30. So we have here 30 and 8. Okay, so we'll do this. How many comparisons are we gonna do? Log n, depend on the height. Okay.
And n is for finding them.
No, log n is the height of the
I
tree.
mean like for Heapify, it's n log n because n like for finding the
No.
maximum here. And
No.
log is for sorry.
No, because n, after deleting share, what I have outside, I have, what was the value? I have 50, okay?
Yeah.
So to get the next highest number, I should delete again, okay? And I'll have 31. To get the next highest number, I'll have what? 30. So I will call delete how many times? N times. What is the cost of delete? Log n. So the final heap sort is n log n, okay? Then when we talk about build the heap, okay?
Okay, so heapify is okay.
Yes.
Heapify n log n.
No, to build a heap, if you build a heap from the bottom to the top,
It's n log n. So why in the lecture, like they said that to construct a heap, we need to, like, it is constant complexity of n log n, like in worst case, n log n. The lecture. Why to construct. So why, like, like on the last slide, the very last slide.
let me check the slide that you're talking about.
Maybe line about sort.
What's the number?
57, 56, 57. It says it's constructed by cube, but it is so it means
Not yet. Wait a minute.
yes, that's what it says. I mean,
You said 50?
56.
56, okay.
Yes.
It said construct the priority queue. Is it the same than build the heap? If you are given a sequence of n elements, okay, and you are asked to construct the priority queue from those n elements, what's the time complexity in the worst case? To construct a priority queue. Yeah. So let's get back here. If you take a look at this implementation, okay, so we start basically from the leaves node, okay, and we try to make sure that it satisfies the heap property. So for each element, okay, we are trying to perform the heapify. When it is bottom up, okay, this is gonna run linear time because for each node, okay, you have to perform one comparison with each children and swap. So when you pick the first node, you compare with the children. Which is the biggest? You swap them, okay? And then you go to the next element. You compare with the children and you swap them. And then you go to the next element, okay? From the last to the root. Let me go here. So when you start from 8, okay? Does it have children? No. You go to 30. Does it have children? No. You go here. Does it have children? No. And then you come here. Does it have children? Yes. Okay. So you can have access to children in constant time. You compare this one, and then you swap. $15. Does it have? Yeah, but it has 8, right? If you take 15, oh yeah, 15 does not have, but 9 does have 8. Okay, so we check and then we swap. Okay, and then we go to 30, we check its children, which are these two. Okay, and then we swap. Yeah, all constant operation. So you are doing it in linear time, basically.
Yes. And the swap is is to is a constant time.
Yes, all of those operations are constant.
Yes, yes.
So what's the finite time complexity to build a heap?
You can check the same for 0 index.
For 15? Yes, so what are the children? No, 20, 21, these are the children.
And after that, we will check the same for 20 and 21.
Then you are doing what? Top down. You are shifting top down. Okay. Yeah.
After all the slopes, yes, we need to go from the top to the bottom. Yes.
When you reach 20, when you hit 50,
yes, after all the slopes, after all the points, yes, we need to go to the bottom.
you need to go to the bottom. Yeah, intuitively, you have already the maximum
Yes.
in the top. Okay.
Because we have branch from the top.
Yes, you should go to the bottom because it can be like the lowest element
Yes.
that is there. Okay.
The worst case.
You have what? You have one operation that may take log n. And what is the other operation? What are the other operations? Linear with the big O notation. Yeah, it can be seen as a plus, for example. Okay. Yeah. So let's check. Let's resume like the heap sort algorithm. First, you need to build the max heap. Okay. Building a max heap, given a sequence. What is the time constant of building a max heap? If you are given a sequence and you're asked to solve the sequence, you have to build a max heap.
Yes, then
If you are given the sequence 12, 0, I don't know, 20, huh?
Should be n log n.
It's n log n. If you are given the sequence, you should not confuse the fact that you are given a tree, okay, and you're asked to AP5. Okay. So if you do it element by element, okay, we are having n log n. Okay.
each element log n times because we keep it.
Yeah, because we heapify n time.
But we said that heapifies that.
Build heap. Yeah, if you have to build a heap, okay, from a binary search tree.
Yes, yes. This is the main difference that I was confused.
Yes.
This is like the task was in the heap sort. Yes, we are given sequence and we are building
from that sequence, you build the heap.
Yeah, the heap.
Okay.
Yes.
So from that sequence, you build a heap. It's n log n.
And from the binary tree to build or some complete binary tree to build the heap.
What?
From the complete binary tree to build the heap. What is the
If you have a complete binary tree, okay, you can build the heap in linear time when you perform it bottom up. Okay. So when you have a sequence, let's say this is the sequence, and you are asked to use heap sort. The first thing that you have to do, you have to build a max heap. What the time complexity is n log n. Okay. Next, you have to repeat this n times. Okay. What do we need to repeat? Delete the root element. Okay. And heapify. So delete the root element. This is, let me put it like this. So delete the root element. This is constant because it's just swapping. Okay. Heapify. It's log n. Okay. Decrease the size of the heap. This is constant. And we repeat this how many times? N times. Okay. So this gives us n log n. Okay. Yeah, so you finally have n log n plus n log n. Okay, so you have big O of n log n. Does that make sense? So, Paulina, did you understand why you have n log n? So heap sort, first step, you have to build the max heap. Okay, building a max heap is n log n, because when you insert an element, you have to heapify. Okay, heapify is log n. So in the worst case, after building the entire heap, you have n log n. Then you have to delete the root element n time. Okay, by deleting the whole element n time, you have first delete the element, heapify from that element, which is log n. Okay, you decrease the size of the heap, and you do this until you have no element left in the tree. So you are heapifying n time. So you have n log n plus n log n. With the big connotation, the finite time complexity is just n log n.
Explicitly, it's like a significant to say explicitly whether we're building the heap from the tree and whether we are building.
Of course, that will be clearly mentioned.
Because here in the first part, we are
You have an example here. So go ahead and run this example. Sort the following numbers using heap sort, and we want to see the intermediary steps. Okay. So first thing, build a heap from this. All of you, please take a piece of paper or on your planchette. So first, build a heap from this sequence. Okay. And then delete all the nodes. A max heap. Yes. So before the end of the lab, I want to see from all of you, I want to see the max heap of that sequence.